Okay, let's dive right into this explainer. Today, we're going to decode the absolute magic, well, the engineering mechanics, behind precise mechanical movement. Seriously, if you've ever watched a 3D printer flawlessly build a complex shape, layer by layer, or seen a robotic arm assembling a circuit board with a literal microscopic accuracy, you're looking at the direct result of some incredibly clever electrical engineering. We're zeroing in on exactly how that works by exploring the control of two major players, stepper and servo motors. So to really understand robotic movement, we've got to ask a pretty fundamental question. How do machines solve the problem of imprecise motion? I mean, think about it. If you just hook a standard motor up to a battery, it basically spins wildly, like a toddler on a sugar rush, until you cut the power. You definitely can't use that for precision robotics. You need to control exactly where that motor stops and starts. And this challenge brings us to two brilliant, yet completely different engineering solutions: steppers and servos. Section 1. Stepper motors explained. Let's look at this first path to precision, which is built entirely on the concept of absolute, rigid, mechanical certainty.
So, stepper motors. These guys convert electrical pulses into exact, discrete mechanical movements. It's actually a lot like walking up a staircase, one fixed step at a time, rather than just sliding up a smooth ramp. Now, depending on what a machine needs to do, engineers generally use three main types of steppers to pull this off: variable reluctance, permanent magnet, and hybrid motors. But here's the kicker. Across all three of these types, the basic idea is the same. You send a single electrical pulse, and the motor responds with one distinct click of rotation. So if you want to control motion and position with pinpoint accuracy, you simply have to count the pulses you're sending.
And depending on the specific design of that motor, with every single electrical pulse supplied to a stator winding, the motor advances by a highly specific angle. That could be a massive 90-degree turn, 45 degrees, 18 degrees, or even a tiny fraction of a degree per pulse. We're talking so small you'd literally need a microscope to see the gear actually move. Because the physical design of the motor itself dictates this angle, the movement is incredibly reliable. It's a simple rule. One pulse equals exactly one step, period. Now, let's talk about the math behind that movement, specifically the force of attraction equation. This equation shows us the force between an energized phase of the stator and the rotor itself. F is our force, mu is the absolute permeability, d is the air gap distance between the stator and the rotor, and I is the current of the winding. But I want you to pay special attention to the current I. Notice how it's squared. Because force increases with the square of the current, just adding a little more electrical juice provides a massive exponential increase in mechanical push. This is exactly how engineers can tune these motors to snap into those discrete steps with such incredible authority. Section 2. Calculating step angles. So the crucial point here is figuring out exactly how these motors divide a full circle into those precise individual steps. There are two foundational concepts that define this movement. First, we have the step angle, which is exactly how far the motor shaft turns on a single isolated electrical pulse. Then we have the steps per revolution, and that dictates how many of those tiny individual steps are actually required to complete a full 360-degree rotation. It's pretty straightforward. If you know one, you can easily figure out the other. But how are these numbers physically built into the motor in the first place? Well, to engineer that precise step angle, designers rely heavily on two physical variables. The first is NPH, which stands for the number of stator phases. That's basically the separate electromagnetic coils surrounding the spinning center. The second variable is NT, which is the number of teeth physically present on the rotor itself. By mathematically varying the number of magnetic coils against the number of physical teeth on that gear, engineers can perfectly divide a 360-degree circle into those exact fractions we were just talking about. Moving on to Section 3, the art of ramping. Now, this is where we run into a really fascinating real-world physics problem. How do you handle that discrete, step-by-step precision when the machine has to move incredibly fast? Just imagine a motor slowing, which, by the way, is the engineering term for its high-speed operating state, at a blistering 5,000 steps every single second. To put that into perspective, a hummingbird beats its wings about 80 times a second. So at 5,000 steps, this motor is absolutely flying. But remember, a stepper motor is supposed to move perfectly in sync with its electrical pulses. If you just instantly cut the power to a motor doing 5,000 steps a second, yeah, physics takes over. The physical inertia of that spinning rotor means it cannot possibly be brought to a dead stop in a single step. It would skip steps, lose its place, and your machine's perfect precision would be totally ruined.
So, because you can't just stop instantly at that kind of speed, engineers use an elegant solution called ramping. During the acceleration phase, there's a progressive increase in the number of driving pulses per second to safely get the motor up to speed. Then it hits that high-speed slewing state. Finally, to stop, it goes through a gradual deceleration. Now, this whole ramping process is usually completed in a fraction of a second, but it is absolutely vital. It ensures that the instantaneous position of the rotor always exactly corresponds to the number of pulses sent, which preserves that perfect accuracy.
All right, section 4, servo motors and feedback. Now we're going to shift gears to our second path to precision, which takes a radically different, highly self-aware approach. The contrast between these two technologies is honestly stark. Stepper motors are what we call an open-loop system. They step blindly forward on command, basically just trusting that the mechanics worked out. Servo motors, on the other hand, are closed-loop. They act with constant self-awareness. A servo motor is essentially a standard DC motor, but its output shaft is coupled to a potentiometer. And this potentiometer acts as a sensor, continually feeding the motor's actual physical position back to a control circuit. Because of this continuous feedback loop, the servo is constantly calculating the difference between where it currently is and where the input signal is telling it to be. The control circuit actively drives the motor until that error, meaning the difference between the reference input and the potentiometer signal, is exactly zero. This guarantees the output shaft achieves the precise desired angular position. Plus, servo motors incorporate internal drive gears. By calculating the gear ratio, which is dividing the number of teeth on the output gear by the input gear, engineers actually multiply the motor's native torque. This allows them to precisely maneuver much heavier loads than a direct drive setup could ever manage. Section 5, controlling with pulse widths. This brings up a really interesting question. How do we actually communicate with this self-aware servo? How do we tell it where its target angle is? Well, we command it using a specific control signal based on pulse width. Think of it as a spectrum of electrical instructions. When you send a minimum width pulse to the servo, it reads that and quickly drives the motor to one extreme physical position. If you send a maximum width pulse, it drives all the way to the exact opposite extreme position. And a neutral pulse, that will center it perfectly right in the middle. By varying the width of the electrical pulse anywhere along this spectrum, you can command the servo to stop at literally any precise angle in between. But here's the thing. The job isn't done once it reaches that target angle. Once a servo moves to the correct position, you can't just cut the power. You actually have to maintain that specific position pulse. Maintaining that signal is what commands the servo to actively hold its ground. As long as it receives that pulse, the control circuit will vigorously fight any outside force trying to move it, exerting its maximum rated torque to stay exactly where you told it to be. It's an active, continuous process of maintaining precision. Which brings us to a really fascinating crossroads in mechanical design. On one hand, we have the stepper motor, relying on rigid, calculated, open-loop mechanical steps. And on the other, we have the servo motor, relying on constant, closed-loop sensing and active feedback. The next time you see a robotic arm on an assembly line, or a 3D printer meticulously crafting an object, take a second and ask yourself, which of these two incredible paths to precision is bringing that machine to life? Are we stepping with mechanical certainty, or sensing and adapting to the physical world? Thanks so much for joining me on this explainer, and definitely keep questioning how the world around you actually works.